All right, hello again. Today we are looking at acids and bases. And we've talked a little bit about acids and bases way back in a previous video when we were talking about certain structures and naming of acids. And so we're going to be looking at acids and bases and particularly how they behave in water. It's actually how you create an acid or base is you're going to take a certain compound and put that into water. And one of the definitions of an acid or base is what happens when you put these compounds in water. There's going to be certain things that are produced, and an acid will produce something in water, a base will produce something in water. That is one way to define an acid and a base, and we're going to be looking at that today. They play a very important role in our lives, meaning those acids and bases. You see them all the time. There are numerous biological processes, industrial applications, environmental problems, all a result of the function of the acidity or the alkalinity, that would be for the base, of aqueous solutions. Okay, so it's important to understand these when we're talking about chemistry because they are so prevalent. And these acids and bases, they behave in a particular manner when they are put into water. So in this activity, we're going to look at the physical and chemical properties of acids and bases. Model 1, we're going to be looking at acids and bases, and in particular how acids and bases are defined according to a scientist whose name was Arrhenius, and we're going to be looking at how they are defined as they are put into an aqueous solution. This is how Arrhenius defined them. Here is some common acids and bases, their chemical formula, where they may be found, how they taste, what they do with litmus paper. Litmus paper is simply paper that is coated with indicator, a kind of chemical that is going to change colors depending on how acidic or how basic that solution is. Does it conduct electricity, and is it an acid or base? We're kind of testing these different solutions over here and then determining if they are an acid or if they are a base. What is the common chemical name for vitamin C? So we have different chemicals here, vitamin C, and the name for that is ascorbic acid. Is vitamin C classified as an acid or base? We have it classified here as an acid. Examine the properties of the Arrhenius acids in Model 1. List 3 properties that all Arrhenius acids have in common. Okay, so let's look at the acids. It seems to be the first group here, and let's see if we can determine some things that are unique about acids as we look at this model. Well, how do they taste? They all taste sour. They turn litmus paper red. And you also may notice that they conduct electricity, but that's not unique to acids. Bases do as well. Remember, these are in aqueous solutions, and when you put ionic compounds in aqueous solutions, you are going to form ions. And ions are charged particles, so it makes sense that that solution is going to conduct electricity. Okay? Let's look at something else that is common. Not always in an acid, but in this case, notice what we have in these acids. They all have an H in them. Some of them have 1 H, 2, 3, but they all have H's in them. So those would be 3 things. So they have H, they are sour, and they turn litmus paper red. Examine the chemical formulas for the Arrhenius acid in Model 1. What feature do all the Arrhenius acid chemical formulas have in common? As mentioned already, they're going to have an H predominantly at the beginning of their chemical formula. Okay? Examine the properties of the Arrhenius base. List 2 properties that all of the bases have in common. So you could put that they taste bitter. Obviously, you don't want to be tasting these. They turn litmus paper blue. Okay? And chemically, what do they have? Chemical formula for the bases. you're going to see the hydroxide ion for the bases. So the H plus, this is just a proton. H plus is a proton. Proton for the acids, hydroxide for the bases. So if you dissolve a small amount of baking soda in water and tested it with litmus paper, and the litmus paper turned blue, is it likely an acid or a base? So if it turns the litmus paper blue, that is a good test that that baking soda is a base. So in 1903, Mr. Arrhenius won the Nobel Prize in Chemistry for defining acids and bases in terms of the ions that are produced. So these are in aqueous solutions. When they are in aqueous solutions, they break apart into ions. And therefore, if we say an Arrhenius acid, this is how he defined it, is any substance that when you put it into water is going to produce hydrogen ions. So an acid is going to produce H plus. So that's why all in the formula you see the H in the formula. So when you put it into water, it breaks apart into ions and the H plus is released. Now actually that H plus, because it's in water, it combines with water molecules to form H3O plus, and that is called hydronium. Okay, so H plus is, as far as an acid goes, if we just say H plus for an acidic solution, what we really mean is the hydronium. We're just saying H plus because we understand that water is a part of it as well. Okay, we've just kind of left out the water. So hydronium ion. And an Arrhenius base is any substance that when you put it into water, it's going to break apart into ions, and one of the ions that it forms is a hydroxide ion. So a base is going to have hydroxide formed in water. Okay? So while Arrhenius definitions of acids and bases are useful, they are a little bit limited. Okay? They're restricted because they're saying it has to be in water. This is what happens when you take that particular substance and you put it into water. Okay? Now we have another definition. Mr. Bronsted and Mr. Lowry come along and they develop something that is just a little more general. So what they're saying is, well, let's broaden our definition. What if we don't put it into an aqueous solution? What if we don't make an aqueous solution? Is it still an acid or a base? Let's define it using what it does in a chemical reaction. So here's how Bronsted and Lowry define an acid and a base. We're going to look at this model to help us with this. Really what they're saying is, let's see how it reacts. What does an acid do in a reaction? What does a base do in a reaction? So we have 4 reactions here, and we're going to analyze these and see what happens. Identify the Bronsted-Lowry acids in Model 2. Well, they are labeled for us. So acid, 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 and acid. Atoms of which element are present in all of the Bronsted-Lowry acids? Atoms of which element? So you've got H, H, 2 H's here. Oops, sorry, wrong one. H, okay, and H again. So you're going to have the hydrogen. How can you tell from reaction 1 that HCl loses an H plus ion rather than a hydrogen atom when the reaction occurs? So we're going to look at the products here. So again, we're looking at this and we're saying, how can we tell from reaction 1 that the HCl, that's hydrochloric acid by the way, loses the H plus rather than a hydrogen atom when the reaction occurs? So if we look here, this H, we're going to find out what happens to it. We're going to compare the reactant side over here to the product side over here. Notice all of these are neutral. There are no charges on these. Now the reaction occurs and all of a sudden we have charges. Well, how did that happen? HCl, if you put that into water, will break apart into H plus ion and Cl negative ion. the hydrogen ion and the chloride ion. This H plus then is going to combine with the water and make the H3O plus. See the plus there? That came from the H plus. And the Cl negative is all by itself as a charged particle and ion. So that's how we know that it is donating an H plus and not just an H. Okay? So an acid in a reaction is going to do what? It'll donate an H plus to something in the reaction. For each acid-base reaction in Model 2, describe the role of the Bronsted-Lowry acid in the H plus ion proton transfer. So what does it do? I just mentioned the acid will always, as you look at the reaction here that involves an acid and a base, the acid is always going to be the one that on the reactant side has an H, and on the product side it gave up its H to the base. So it always is going to donate the H plus. It's always going to donate an H plus and then form these products on the other side of the reaction. The acid is always going to donate H plus in the reaction. For each acid-base reaction in Model 2, describe the role of the base. Well, then the base, something's got, if the acid is going to donate the H plus, then something has to accept it. The base is going to then accept the H plus. Okay, so let's look back up here again. The HCl, in order to create these products right here, how did these products get formed? Well, the H from the HCl went to the water to form the H3O plus. And the Cl negative is left behind because the H was given to the base, which is the water. So the acid donates the H plus to the water is acting as the base, is receiving that, forming the hydronium, leaving the Cl negative ion by itself. As you saw in Model 1, all Arrhenius bases in Model 1 have the hydroxide ion in their chemical formulas. Write a balanced chemical reaction for the reaction of HCl and hydroxide in an aqueous solution to illustrate that the hydroxide ion is also a Bronsted-Lowry base. Okay, so basically, if we take HCl and we're going to react it with hydroxide, so we've got HCl and hydroxide. This hydroxide has to come from something. So you took, like for example, sodium hydroxide and you put it into water, and it's going to create then the sodium ion and the hydroxide ion. Okay, so we're saying we have hydroxide ions in our solution somewhere. Okay, that's what that's coming from. And then we take some HCl and we put that in there as well. What's the reaction that's going to happen here? Well, the balanced chemical reaction for HCl and hydroxide, this is your acid, and that acid has an H in it, which is going to donate to the hydroxide. What is that going to form? H2O, H plus and OH negative is going to be H2O, and what's that going to leave behind? Cl negative. Interesting. So that must mean when you've got acids and certain bases that have hydroxide in them, this is your base, what is going to form? Water and then some other ion or some other particle, in this case, this is your chloride ion. Okay? So the H plus and the hydroxide ion actually form water when they get together. But it is the OH negative, the hydroxide, that is accepting the H plus, so it's acting as the base, and is HCl that is donating the H plus, so it's acting as the acid. If you reverse reaction 1 in Model 2, the following reaction is obtained. So this time we're going to flip it around. We've got the hydronium here, plus the Cl negative is going to create the acid and the water. By the way, double arrow, what do you think that means? Double arrow means it can go either direction. This is a reversible reaction, right? We talked about that in the previous video when we talked about equilibrium. So both directions are occurring and will continue to occur until it reaches equilibrium. All right, for the reaction above, which reactant is acting like a Bronsted-Lowry acid? How can you tell? And down here we're going to say which one is acting like a base. How can you tell? All you have to do is follow the H plus. Follow the H. Wherever the H is going, that tells you who's the acid and who's the base. Wherever the H is, and whoever is giving up that H plus is your acid. Whoever is receiving the H plus, that is your base. In order to go from one side to the other side for an acid-base reaction, the H plus has to be donated and the H plus has to be received. Okay, one species is donating, one species is receiving. So we just have to see who's doing that. Well, in order to go from H3O plus and then over here have H2O, this H3O plus has to give up an H plus. Who does it give it up to? The chloride ion, because here on the reactant side you have chloride ion, but now all of a sudden you've got HCl. So that chloride ion must have accepted the H plus. So this is your process. The H plus then is donated from the hydronium to the chloride. We can now identify which is the acid, which is the base. The hydronium is your acid. Cl negative is acting as the base. I know the Cl negative doesn't have OH in it. I know that. Okay? But this is the definition. The OH negative definition was Arrhenius. Arrhenius said that you have to create the hydroxide ion when you put it into water. Bronsted-Lowry is saying, well, that's not always how we define a base. A base is whichever species is going to accept a proton in the reaction. And the acid is whichever species is going to donate that proton, meaning H plus. Okay? So they have a broader definition of an acid and a base. Write the reverse reactions for reaction 2 and 3 in Model 2. Label the acid and the base. So we're going back up to Model 2, reactions 2 and 3, and we're going to reverse them. Okay? So we're going to take these right here, 2 and 3. We're going to reverse them. I'm going to put a double arrow because these are really reversible reactions. Okay? And I'm going to take reaction 3 and just write this one right now as well. We got hydronium and ammonia. I'm going to leave that one right there like that. I'm going to show you how I can predict what the products are. So basically, let's look at reaction number 2. It says write the reverse reactions for them, and now we're going to label acid and base. So all we have to do is follow and see what happened to the H plus. Well, on the reactant side here you've got F negative, and now all of a sudden we've got HF. That must mean that that F negative, that fluoride ion, accepted the H plus in order to create your HF. So the H plus went from what? Went from the ammonium ion to the fluoride ion. So your ammonium is your acid. That is donating H plus to what? The fluoride ion, so this must be your base. Oh, and by the way, remember originally, if we have the other direction here, it was the ammonia here that was your base, and your HF is the acid because the H was donated this direction in order to form these products. So if we go the other direction, backwards, this H here and the HF would be donated to the NH3 to form the NH4 plus. So this would be acid, and this would be base. So we have, depending on which direction you're going, we're always going to have an acid and a base in one direction and an acid base in the other direction. Okay? So that we don't get them confused, the reactant side, you have an acid and a base, and on the other side, these actually are sometimes called the conjugate. Conjugate base and the conjugate acid. That word is conjugate, like this. Okay? So the acid here on the reactant side is actually going to turn into a base on the other side for the reverse reaction. And the base here as the reactant is going to turn into the acid on the other side for the reverse reaction. Okay? So you pair them up. An acid base conjugate pair. A base acid conjugate pair. Okay? Here we have a hydronium and the NH3, the ammonia, and in this case, I know that hydronium is the acid. It's going to donate to the NH3 to form NH4 plus. The hydronium then, if it donates its H plus, it's going to turn into just water. And that's what's going to happen there. So in this case, this is your acid. It turns into water, which is going to be your conjugate base, and the NH3 is accepting the H plus, so it's acting as a base over here, but it's going to turn into NH4 plus, which if in the reverse reaction, if you look at the reverse reaction, to go in the other direction, the NH4 plus would donate the H plus back to water to form the hydronium, so it's acting as an acid in the reverse direction. Okay? And you compare these up. The hydronium H3O plus became water, so the acid hydronium ion became water, which is acting as the base in the reverse reaction. That's a pair. And here's another base and conjugate acid pair. Those are paired up too because one comes from the other due to the transfer of that H plus. Okay? Here we have indeed our conjugate acid-base pairs. So you're going to see as this reaction occurs that the base turns into an acid for the reverse reaction, and the acid is going to turn into a base for the reverse reaction. All acid-base reactions have two conjugate acid-base pairs. One conjugate acid-base pair in the reaction in Model 3 is the hydronium and water. List the other acid-base pair in the reaction. So we're looking at Model 3. One combination is the hydronium. This is one pair here. The other pair then would be the CO3 negative and the HCO3 negative. Okay? By the way, you know they're pairs because they're going to differ by what? They're going to differ by an H. Okay? And the charge is going to be one less. So notice, this one has an H in it, this one has no H. This charge is one less than the other one. Same thing with the pair here of hydronium and water. The water has one less H in it, and its charge is one less as well. Okay? Because there's a transfer of H plus. Why is HCO3 negative considered the acid part of the pair? Because it is on the reactant side. So this is the acid. The reaction here, these are the reactants on this side. So if these are the reactants on the left side, we're considering the reaction going from left to right. Okay? So we're going to write this as the acid because we're looking at the reaction as it would occur from left to right. I know this is the double arrow, but just for standardizing this, the reactants are on the left always, products are on the right, so the acid is going to donate the H plus to the base forming our products. What is donating to H plus as you go from left to right? That's the standard way of thinking of it. Okay? So this is donating H plus as we look at the reaction from left to right. And the CO3 2 negative is considered the base because it is in the other direction. Okay? The other direction is going to be receiving an H plus if you look at the reverse direction. Okay? This is a base as well, of course. Okay? But in the reverse direction, this is your base. Alright? So acid, conjugate base, base, conjugate acid, they're always paired up, and you just have to follow, I'm going to emphasize this again, just follow the H plus. That is going to tell you who is who. Acid always donates to H plus, base always accepts it. Okay? So Model 2 calls the transfer of H plus ion a proton transfer. Explain why H plus ion and proton are synonymous. Well, hydrogen is an atom that has one proton in its nucleus and one electron. And if you remove this electron, it's gone. Now you form H plus an ion because you got rid of the negative electron and you just have the positive proton in the nucleus. Well, that's all this is. It is simply just a proton. It has no electron on it at all. So H plus and proton mean the same thing. Examine the charges on the species in the Model 3 reaction. Why does the charge on the carbon containing ion change from -2 to -1 to -2? So as mentioned there, that when you take away an H plus, then the charge is going to drop. So let's just dive into this a little bit more. Model 3, the charge on the carbon containing ion. Okay, so if you look back up here, and here, contains carbon. It's going from -1 to -2 because it is losing its H plus. It's giving up a charge. It's giving up a +1. If it gives up a positive charge, then what remains is more electrons than protons. You just gave up a proton, you've taken away, you've given up positive charges. So the charge is going to become more negative. It's going to drop. Okay? Using the list of substances below, select pairs that are conjugate acids and bases. Enter the pairs in the table below. The first acid-base pair has been entered for you. Note that you may use a substance more than once or not at all. All you need to do to see the pairs is notice that there's going to be a difference in the number of H's by 1 H, and the charge is going to be a difference by 1 as well. The one that lost the H, the one that has one fewer H, the charge should be more negative. It should be a little bit, one less, more negative. Okay? So, kind of complicated that. Let's look at our examples here. So H3PO4, and if that loses an H plus, it's going to turn into H2PO4 negative. Notice how the charge became 1, it dropped by 1. Okay, we'll say that. Let's take another one. If I took care of that one, and that one. All right, let's take H3O plus, and if that donates its proton, what's left behind? What's left behind is H2O. So the H is reduced by 1, and the charge drops by 1. Okay? Let's take H, C2H3O2. That is acetic acid, and if it donates this H right here, then it's going to just become this ion without the H. Okay? Let's find something else that has H in it. Here we have this one, H2PO4. Oh, we did that one already, didn't we? Oh, I'm sorry, I used this up. I used this one up. I didn't use this one up yet first. Okay, I didn't use this one up yet. So actually, let's take this one. Okay, and if this gives up an H, then it's still going to have one H left behind because it's only giving up one at a time, and the charge will drop by one. So there, I did use this one, and now I did use that one. Okay. Let's take this one. If it gives up an H, it's going to have one left behind, and its charge is going to drop by one. Okay? I don't see that as an option there, but that's what it would be. If we have HPO4, 2 negative, that still has an H in there. That's this one. I used it before, but I could use it again now because it still has one more H, and then gives up its H and would reduce its charge by 1. Okay? You could have water. Water can act as an acid or a base. It's amphoteric. Acid or a base, if it gives up an H, what's going to be left? Just one H and the O, that's a hydroxide ion. Because you can write water as HOH. We don't usually write it like that, but it is basically HOH. If this H is gone, it leaves behind the hydroxide, and so you've got another pair there. Okay? Alright, so there's possible combinations. Write the formula for the conjugate base of each of the following acids. Be sure to consider charges. Don't forget, the H, the number of H's is going to drop by 1, and the charge is going to drop by 1. There, it's that simple. Okay? I was making it so complicated before. Alright, so if this is the acid and we're going to write the conjugate base, then this would turn into SO3, 2 negative, we lost the H. This would turn into just F negative, and this would turn into S2 negative. The H plus is gone, the charge drops by 1. Write the formula for the conjugate acid of the following bases. This time, we're going to add an H, and the charge is going to go up by 1. So this is going to turn, if this accepts a proton, it's going to become HSO3 negative. Don't change the formula of the SO3. Just add an H and increase the charge by 1. Here, add an H, and if it's a negative 1, it becomes 0. H, add another H, and increase the charge by 1, so this becomes 0. For the following reactions, label the acid and base in the reactants and the conjugate acid and base in the products. Okay, just follow, I know I said this already, follow the H plus. Keep it simple. So, in this case, to go from reactant side to product side, look what happened. The HCO3 negative lost its H. So that must mean that this is donating its H plus to the NH3. This is your acid. This is your base. And the acid, after it donates the proton, it becomes the CO3 2 negative. So this is your conjugate base. And this is your conjugate acid. You also can look at the reverse direction if you want to confirm that this is indeed the acid and the base on the product side. Because if the reverse reaction happened, how would you go in the opposite direction? Well, this NH4 plus would have to donate the proton back to the CO3 2 negative to form what you have on the reactant side. So in this case, to get the reverse reaction to occur, you would have to have the proton donated from the NH4 plus to the carbonate ion. Okay? All right, and here, in order to get our products, in order to get this Cl negative, there's an easy way to see this. Then the HCl must have given up its H. So in this case, proton is given there. So this is your acid, and it would then become, it turns into the conjugate base. This must be your base because it's accepting the proton, and it would turn into, on this side, for the reverse reaction, the acid. Is the role of the conjugate acid in the reverse direction the same as the role of the acid in the forward direction? Yes, it donates H+. That's exactly what the acid does in the Bronsted-Lowry definition of an acid. The base is the proton acceptor, the acid is the proton donor. All right, extension question. Some of the substances used in this activity can behave as both an acid and a base. I mentioned one such substance, water. These substances are said to be amphiprotic or amphoteric, as I mentioned. Okay, I think I said amphoteric, but either term is fine. Provide 2 examples of amphoteric substances found in this activity. So water was one of them. I think if you look back up in the reactions, you'd also see that NH3 acts as an acid or a base in some cases, and there might be others as well. So just look back up there and see in our reactions if we labeled some both as an acid, but then maybe in a different reaction it was labeled as a base. Okay? So it depends on what it's reacting with. What it's reacting with is sometimes going to determine whether it acts as an acid or a base. Water is an amphoteric substance. In any sample of water, some of the molecules perform acid-base reactions with each other. Meaning if you've got water, just water, water will react with itself. This is called auto-ionization. Auto-ionization of water simply means that this is to a very, very small degree, by the way. Not every single water molecule is going to react like this in a sample of water. A small, minute quantity of them do this. But basically, one of the water molecules will react like an acid, donate its H+ to the other one, thus the other one is acting like a base, and what is formed? Well, if water gives up its H+, it becomes hydroxide. And if water gains an H+, it becomes hydronium. Look at that. We actually have hydronium and hydroxide both in existence in pure water. This now, if you look at the reverse direction, this would be your acid, this would be your base, and these are your pairs. Okay? So that is called the auto-ionization of water, and happens all the time in every sample of water to different degrees depending on the temperature, but always to just a very slight quantity, but it still is very significant, and we'll talk more about that as we talk about acids and bases and the strengths of acids and bases in the next video.